Okay, so in this video, we will have a look at some of the instructions in 8085 microprocessor. Okay, so let's start. So what I would suggest is you pause the video and you copy everything down. Okay, so I hope you have copied down the parts. Now what I'll do is I'll dictate the description part and I'll dictate the flags part. Okay, I hope you have copied down till this point. Let me dictate the description. So you can write down against description, please write the 16-bit contents of the specified register pair are added to the contents of the HL register and the sum is saved in the HL register. The contents of the source register pair are not altered. I'll repeat once again. I'll repeat the description part. The 16-bit contents of the specified register pair are added to the contents of the HL register and the sum is saved in the HL register. Full stop. The contents of the source register pair are not altered. Now, against flags, please write down, if the result is larger than 16 bits, the carry flag is set. If the result is larger than 16 bits, the carry flag is set. Full stop. No other flags are affected. Full stop. Now let's have a look at this example. See, this is the DAD instruction. DAD stands for double byte addition. Okay, we are trying to do double byte addition. By double byte addition, what you mean is you're trying to add two 16-bit numbers. Okay, and now how is this special? This is special because you'll be doing it on register pairs. Now here, the destination register pair is considered to be the HL register. So what you can do is you can consider any of the other register pairs. What are the possible register pairs that you have? BC, DE, HL and the stack pointer. So what you can do is you can take the contents of the BC register, add it with the contents of the HL register and store the result in the HL register itself. Look at this, look at the addressing mode. Okay, so this is a 1 byte instruction. The opcode is DAD. This is what the instruction does. It adds register pair to H and L registers. You will see this in the example shortly. And what about the addressing mode? The addressing mode is register direct. If you consider the source, if you consider the source of the operand, see what is the operand? The operand is register pair. So with respect to the source, the addressing mode is register direct. And the destination, what about the destination register? The destination register is implied to be the HL register itself. See, add register pair to HL register, and as I pointed out in the description part, the contents of the source register pair are not altered and the contents of the HL register are added with the contents of the register pair and the result is stored in the HL register itself. Okay, so since the result is stored in the HL register itself, the destination is implied to be the HL register pair. Now let's take an example. See, in this example, they're saying, say HL contains this hexadecimal value 0242H. Now you want to multiply it by 2. Now if you want to multiply the content of HL by 2, it is same as adding HL to itself. So what will be the instruction? The instruction will be DAD-H. So DAD-H would mean, DAD-H implies that in your HL register pair, you will be storing the sum of HL and HL. Okay. See, one of the operands, see, I'm saying DAD-H. H here represents the register pair HL. So I'm taking the register pair HL and the other operand is assumed to be HL itself. And where am I storing the result? I'm storing the result in HL itself. So if I add a number with itself, what will I get? I'll get double the value. So see, initially the value of HL register pair is 0242. Now if I add these two numbers, like if I add 0242 with itself, because HL is 0242, again HL is 0242. If I add these two, I'll get 0484. And what is the result? The result is in this form. Okay, so I hope you have understood this. What I'll do is now I'll take up the next instruction, DAA. Let's see. Okay, the next instruction is decimal adjust accumulator. Okay, when will you use this instruction? You will use this instruction if you're dealing with BCD numbers. What happens is, what are the valid BCD codes? The valid BCD codes are 0 to 9. So anything that exceeds 9 will be considered an invalid BCD number. And what would you do? You would add 6 to make it valid again. So in order to make this happen, in order to transform an invalid BCD number to a valid BCD number, what the 8085 microprocessor does is it makes use of this instruction called DAA. That means it makes it available to us. We have this instruction with us, DAA, and using this instruction, we can change an invalid BCD number to a valid BCD number. Remember, this is the only instruction which uses the auxiliary carry flag internally to carry out the check. Okay, so we'll be seeing shortly how the auxiliary carry flag is made use of. So remember, in this instruction, let's say you're adding two numbers and you're dealing with BCD numbers. See, whatever numbers you'll be inputting, they'll all be in hexadecimal. But it can happen that you are dealing only with BCD numbers. So you are interpreting the input to be in BCD. So you will be inputting your numbers in that form. That means all your numbers will be in the range of, like, not all your numbers, it would be more correct if I say every digit of your number will be in the range of 0 to 9, because those are the valid BCD symbols. Now, you have decided to write a program, to write an assembly language program where you will be dealing only with BCD numbers. So every digit in your BCD number or every digit in your input will be in the range of 0 to 9. Now, after you store these numbers, you will be adding them. Now, it may happen that the result, that means the sum, you're adding two numbers, it may happen that the sum is not a valid BCD number. So, in order to make it a valid BCD number, you would be carrying out this instruction DAA. Okay, so it's like this. Let's say I have an instruction. So, I'm dealing with two BCD numbers. So, I say MVI, I move into my accumulator a BCD number called 23H, but it has to be entered in the form of hexadecimal because 8085 only accepts hexadecimal numbers. And let's say I have another register B where I'm storing, let's say 39H. Now what will I do? I'll say add A. If I say add A, what will happen? In my accumulator register, I'll get the sum of A plus B. Now I'm not sure whether this sum is a valid BCD number or not. Whether I'm sure or not sure, it is recommended that after you add two numbers which you are assuming to be in BCD, you write this instruction DAA. Now this DAA instruction, what will it do is, it will internally make use of the auxiliary carry flag to convert an invalid BCD sum or an invalid BCD number to a valid BCD number. Okay, so this is how the DAA instruction works. And now, what will I do is, I'll dictate the description part. You please note it down. You please note down the description. Let me dictate the description part. Please write, the contents of the accumulator are changed from a binary value to two 4-bit BCD digits. This is the full stop. This is the only instruction that uses the auxiliary carry flag internally to perform the binary to BCD conversion. Full stop. The conversion procedure is as described below. Number 1, if the value of the low order 4 bits, D3 to D0, please write it like this, D3 to D0, in the accumulator is greater than 9, or the auxiliary carry flag is set, the instruction, that means DAA instruction will add 06 to the low order 4 bits, Number 2, if the value of the high order 4 bits, what is the range of the high order 4 bits? D7 to D4. if the value of the high order 4 bits D7 to D4 in the accumulator is greater than 9, or if the carry flag is set, the instruction, that means DAA instruction, will add 60 to the high order 4 bits. Will add 60 to the high order 4 bits. Point number 3. If both low order 4 bits, that means D3 to D0, if both low order 4 bits, that is D3 to D0, and high order 4 bits, that is D7 to D4, are greater than 9, if both low order 4 bits and high order 4 bits are greater than 9, we need to add 66 to the entire result. So we'll see all 3 cases. I'll take up 3 examples and we'll see all 3 cases. And against flags, so you have written down against the description part. Now against flags, please write all flags are affected to reflect the result of the operation. So I hope you have written it down. What you can do is you can pause the video from time to time and make your necessary notes. Now let's take the first example where we are trying to add 12. Now here 12, mind you will be entering 12 in the form of a hexadecimal number, but you will be interpreting it as a BCD number. Same with this, you will be entering 39 as a hexadecimal number, but you will be interpreting it as a BCD. So you're trying to add these two and you'll be obviously storing the result in the accumulator. So let's see how the addition happens. So 12 is written as, so 12 is in hex. So I can write it in binary as 0001 for 1, and for 2 is 0010. And what about 39? 0011 1001. Okay. So this is my 12 and this is my 39. Now let's add these two. So it's normal binary addition. So this is 1, this is 1. 0 plus 0 is 0, 0 plus 1 is 1. 1 plus 1 is 0 with a carry of 1. 1 plus 1 is 0 with a carry of 1. This gives me 1 and this gives me 0. Now look at this. Now the high order 4 bits, it's fine. It's within the range. It's between 0 to 9. But look at the low order 4 bits. The low order 4 bits is greater than 9. So if the low order 4 bits is greater than 9, what should I do? I should take this result. Let me write this result here. So I should take this result and I should add, what should I add? If you have noted down the description part, I should add 0, 6. So this is 0 and this is 6. So let me add 0, 6. So if I add 0, 6, I'll get 1, 1, 1, 1. And here I'll get 0, 0. Wait, have I made a mistake here? I think, oh, I'm sorry. This is 1, 0, 1, 1. Oh, I'm really sorry about that. See, this is 0, 1, 0, 0. This is what? This is my result, right? What has my result come to? My result has come to 0, 1, 0, 0 is 4 and 1, 0, 1, 1 is B. So this is 4B, right? 4B, 1, 0, 1, 1. So what should be the addition? So we are adding 0, 6. So I'll get 1. 1 plus 1 is 0 with a carry of 1. 1 plus 1 is 0 with a carry of 1. 1 plus 1 is 0 with a carry of 1. So this is 1, this is 0, this is 1 and this is 0. Now look at this. Now I have a valid BCD number. If you have a look, what you have is this part is 1 and this part is 5. Okay. So DAA internally used this balancing to change my invalid BCD number. This was the invalid BCD number. It changed the invalid BCD number to a valid BCD number. Okay. So I hope this example is understood. I'll take 2 more examples. Let's see. We'll consider all 3 cases. Okay. We're considering all 3 cases. The first one was where we added 12 and 39. I hope you have noted it. You have noted down the example. Now I'll take another example where we'll be adding, let's say 68 with 85. So let's say I'm trying to add 68. Okay, let me change the pen. It's giving up on me. So let me try another one. So I should add 68. So let me add 68 with 85 and let's see what happens. So I'm going to add 68 with 85. Okay. So 68 plus 85. Now let's add. So what is 68? 0, 1, 1, 0. And this is 1, 0, 0, right? This is 68. This is 68. And what about 85? 85 is 1, 0, 0, 0, 1, 0, 1. This is 85. Now let's add. If I add, I'll get 1, 0, 1, 1, 0, 1, 1, 1. Now look at this. Now when I've added 68 and 85, what I have is 1110. So what is the hex of this? This is E. This part is E, and this part is, I think this is D. Yeah, this is D. Now obviously I can see that the high order 4 bits as well as the low order 4 bits, both are out of order. So what I need to do is I need to add 66. This is case number 3 in your description part. So I'll add, you have written down the description, this comes under point number 3. So this is my result. Now I'll add 66. So I'll add 0110 and 0110. So this addition is done like after this comes about. So I have this, let's say I have this number, I'm adding it directly with the accumulator. Then what should I write? I should write ADI, right? Add immediate. So I should say add immediate 68H. Now after doing this, I'm executing the instruction DAA. Because of DAA, because of this instruction, I'm doing this balancing. So let's do this balancing of 66. And this balancing, mind you, is done internally. Whenever I execute this DAA instruction, the 8085 microprocessor checks whether the low order 4 bits or the high order 4 bits, or both low order and high order 4 bits are out of order or not. If they're out of order, what it will do is it will do this balancing. So this is 1, this is 1, this is 0 with a carry of 1. This is 0 with a carry of 1. So this is 1, 1, 1, 0 with a carry of 1. This is 1 and 1, 1, 1, 0 with a carry of 1. Now see. Now this is what? This is my carry flag, right? My carry flag has been set to 1. But look at the 8-bit result that I've got. The 8-bit result is a valid BCD number now. Look at this. This high order 4 bits is now 5 and the low order 4 bits is now 3, which is a valid BCD number. And of course, I need to keep track of the carry in order to get an accurate result. Okay. So I think 2 examples would be good. So the other case would be where you would get to add, I think the first example that I took, I had to add 06. Now another example could be where only the high order 4 bits are out of order. I think you can understand that when the high order 4 bits, when only the high order 4 bits will be out of order, you will be adding 60. When only the low order 4 bits is out of order, you will be adding 06. And when both are out of order, like in this case, you will be adding 66. Now let's take up another instruction. So the next instruction is complement accumulator. Complement accumulator, what will this instruction do? It will simply take the contents of the accumulator, like your accumulator will contain the value in hexadecimal form, right? You will be inputting the number in hexadecimal. What it will do is it will take the hexadecimal value, convert it to binary, take the binary value and perform a complement operation by changing the zeros to ones and the ones to zeros. Okay. So your opcode is CMA, and since the addressing mode, you can understand the addressing mode is implied with respect to source as well as with respect to destination, which means that your complement operation will take place. Your complement operation will take place on the accumulator and the result will be stored in the accumulator itself. And remember, no flags are affected. Because of this instruction, your flags, the 5 flags that you have, sign, 0, carry, auxiliary carry and parity, these 5 flags will not be affected. So against the description, you can write down a line. The contents of the accumulator are complemented. That's all. The contents of the accumulator are complemented, and against flags, you can write down no flags are affected. And if you want, I can take an example. Let's say I have an instruction MVI A, 23H. So this brings this value inside my accumulator. And then if I do CMA, then what will happen? So my accumulator contains You can probably guess the answer by now. So my accumulator contains this value. Accumulator contains 23. 23's binary is this 0010 0011. If I do a CMA, what will happen is, if I do a CMA, the zeros will change to 1 and the ones will change to 0. A simple ones complement operation. So this is 1 1 0 1 and this is again 1 1 0 0. So have I done it right? 0 changed to 1 1 0 1 is 1 1 0 0. Yeah. So what will be the value that will be stored in the accumulator? The hexadecimal of this is, so this is 1101. 1101 is D and 1100 is C. So this will be finally stored in the accumulator. Okay, so I hope this is understood. This was a fairly easy instruction to understand. Now let's take up another instruction. The next instruction is complement carry. So you can understand this opcode that is given is CMC. The operand is none. What this will do is it will not work on any particular register. In this case, it will not work on the accumulator. Remember, this instruction will not work on the accumulator. What it will do is it will simply flip the content of your carry flag. That means if your carry flag currently contains 1 and you execute this instruction CMC, your carry will become 0. And if your carry already contains 0 and if you execute this instruction CMC, it will become 1. So this is what it is, a simple flip operation. So against the description, you can write down the CMC instruction, you can write down against the description, the carry flag is complemented, full stop, that's it. And under flags, you can write down the carry flag is affected, full stop, no other flags are affected. Or you can simply write only the carry flag is affected. And in this case, I have no example to show you as such. You can probably understand what will happen in case of this instruction. So I'll take another instruction. The next instruction is STC, set carry. The previous instruction that we saw was CMC, complement carry, that would take your carry flag and change it to its opposite value. That means if your carry flag currently contained 0, it would change it to 1, and if it contained 1, it would change it to 0. But what about this instruction, STC? See, STC, set carry, it will always change your carry flag to 1. That means if your current carry flag is 0 and if you execute this instruction STC, it would change it to 1. And if your current carry flag is 1 and if you execute this instruction, it will remain 1. The carry flag remains 1. If the carry flag is already set and you execute this instruction STC, it will remain in the set form. So against the description, you can write down for STC, you can write the carry flag is set to 1. Against the description, please write the carry flag is set to 1, full stop. And against flags, please write no other flag is affected except carry. Or you can write except the carry flag, no other flag is affected. So let me take up another instruction. Okay, the next instruction is compare with accumulator, CMP. Okay, so this instruction is very important. From programming perspective, the CMP instruction is used very often in 8085 assembly language programs. So what is it? It is a 1-byte instruction. As you can see, the operand can be in your register, either of the registers, that means A, B, C, D, E, H, L, or it can be in your memory location, which is specified. The address of the memory location is specified by the contents of the HL register. So your operand can either be in register, any of the registers, A, B, C, D, E, H, or L, and it can be in memory, that means in the location which is specified by the contents of the HL register. It's a 1-byte instruction, and if you look at the addressing mode, it is register addressing mode, or register direct addressing mode rather, register direct addressing mode. If you look at the source, if you look at the source of the operand, it is register direct, and it is implied with respect to destination because all operations are performed by considering accumulator as one of the operands. So what will happen is you will take the content of your register. How will the comparison take place? You will take the content of your register or the content of your memory specified by the content of the HL register, and you will subtract it from the content of the accumulator. Now, depending on the value of the subtraction operation, your flags will be altered. and the way your flag is altered will determine whether the content of the accumulator is greater than the content of your operand register, or the content of the accumulator is same as your content of the operand register, or the content of the accumulator is lesser than the content of your operand register. Okay, but remember, always remember that the content of the accumulator will remain unchanged. The content of the operand register will also remain unchanged after the execution of this instruction. The subtraction that takes place is done only temporarily to find the value of the flags, to determine which value is greater than the other, or if both values are same or not. Okay, so this is what the instruction is all about. Now you'll write down this part. Okay, before writing down this part of the description, what I would suggest is I would be dictating a few points. You note that down, and after noting down those points, you copy this, and I'll explain what's going on here. So again, CMP, you can write the contents of the operand, register or memory. Within parentheses, you write register or memory. So contents of the operand within brackets, register or memory, are compared with the contents of the accumulator by performing subtraction, where the contents of the operand are subtracted from the contents of the accumulator. Full stop. Both contents are preserved, and the comparison is as shown in the 3 steps. Now you can write these 3 steps. Okay, so what are these 3 steps? Look at this. See, here it's clearly mentioned that, see, if the content of the accumulator happens to be less than the content of your register or the content of the memory location specified by HL, then what does it mean? Since you are subtracting, what is happening in CMP, what happens is, in your accumulator, or let me put it this way, in your CMP instruction, the register content is subtracted, right? This is what happens. The register content is subtracted from the content of the accumulator, and depending on the value of this result, your flags are altered. So see, if this way, if the subtraction takes place this way, and if your register content happens to be less than the content of the accumulator, what does it mean? It means that accumulator is greater than the register. So if the accumulator is greater than the register, then your carry flag will be 0. And if the content of the accumulator is greater than the content of the register, then obviously the result that you will get will be a non-zero value. And since it will be a non-zero value, the 0 flag will be reset. Now, if the content of the accumulator and the content of the register happen to be the same, then what will happen? Then when you perform the subtraction operation, the result will be 0. Now, if the result is 0, then your 0 flag will definitely be set, and your carry flag will again remain reset. Now, if the content of the accumulator happens to be smaller than the content of the register, then what will happen? Then the carry flag will be set. The carry flag will be set to denote that the accumulator value is smaller than the value of your operand register. And what will happen? Since the result will obviously be a non-zero value, because these two registers or these two operands are not same. Since these two operands are not same, obviously the result will be non-zero. Now, since it will be non-zero, the 0 flag will be reset. Okay, so you copy these 3 points down. Okay, after writing the description part which I dictated, you copy these 3 points down. I hope you have copied it. Now, against flags, please write, all flags are affected to reflect the result of the operation. All flags are affected to reflect the result of the operation. So I hope you have understood up to this point. Now what I'll be doing is, I'll be taking up an example on CMP. Okay, now let's take up an example. Let's say the content of the register B is 62H and the content of the accumulator is 57H, and I'm performing an instruction CMP B. So what will happen? What will happen after the execution of this instruction? Remember, comparison instruction. See, there are 2 comparison instructions. One which is what we are looking at. This is the first comparison instruction which we are looking at, CMP. The next comparison instruction that I'll be taking up shortly is CPI, where the operand is not supplied through your register or memory. It is made available to you directly. right? The CPI instruction we'll see shortly. It behaves in exactly the same way as CMP. But whatever be the case, any comparison operation that you perform in 8085, the contents of your registers will remain unchanged. That means after the comparison operation, B will remain 62 and A will remain 57. The operands are not changed. What is changed is your flags. Your flags will change to reflect the result of the comparison. That means, how will your flags change? Let's see. So how many flags do we have? We have the sign flag, we have the carry flag, we have the zero flag, we have the parity flag, and of course we have the, what am I missing? Sign, zero, carry, parity, and I think I'm missing something. What am I missing? I'm probably missing the auxiliary carry flag. Yes, I'm missing the auxiliary carry flag. I got it. So these 5 flags will be altered to reflect the result of the comparison. All 5 flags will be altered to reflect the result of the comparison. Out of these 5 flags, the flags that would help me to understand the comparison operation are the zero flag and the carry flag. Only these 2 flags are of significance. However, all flags will be affected. All flags will be changed to reflect the result of the operation. But for our convenience, from the programming perspective, we'll be concerned only with the values of the carry flag and the zero flag. So let's see. So now see, I'm doing CMPB. What does CMPB signify? CMPB signifies A minus B. Now obviously, if I'm performing A minus B, or if I'm doing a comparison in this way of A minus B, I have to see which is larger. Now out of B and A, B is larger, so I'm subtracting a larger number from a smaller number. Whenever I subtract a larger number from a smaller number, the result will be non-zero, and since the result is non-zero, the zero flag will be reset. When I'm subtracting a larger number from a smaller number, the carry flag is always set. So the carry flag will always be set. When I'm subtracting a larger number from a smaller number, the result will be negative. And how do we denote negative numbers? The sign flag will be set. And what about the comparison if I perform 57 minus 62? If I perform 57 minus 62, I'll get a negative number, right? Now I have to perform this. So you can understand, if you do 57, you have to convert it to binary. So what is 57 in binary? It's this and this. And what is 62 in binary? 62 in binary is this, right? So what would you do? How would you perform the subtraction? You will take the 2's complement, right? You take the 2's complement of 62 and then you would add it to 57. And then, okay, let me do it for you. Okay, so if I take the 2's complement of this, let me take the 2's complement of 62. If I take the 2's complement of 62, what will I get? So I'm doing it directly. After I get the first one, the remaining things will be complemented, right? So this will become 1, this will become 0, 0, and this will become 1. Now, I don't need this for now. So I'll be adding these two. So let me add these two. So I'll get 1. 1 plus 1 is 0 with a carry of 1. 1 plus 1 plus 1 is 1 with a carry of 1. 1 plus 1 is 0 with a carry of 1. So carry has been generated from the 4th bit. Since a carry has been generated from the 4th bit, the auxiliary carry flag will be set. Now, 1 plus 1 plus 1 is, of course, 1 with a carry of 1. And then this will again generate 1. This will give me 1 and this will give me 1. Quite expectedly, I did not get any carry. Quite expectedly, I did not get any carry. So, okay. Yeah, I did not get any carry. As a result, what will happen is, now see, you might wonder that I haven't got any carry. Now, this is a good question that you may ask, that I haven't got any carry from the addition. That means after performing the 2's complement subtraction, I did not get any carry. But in spite of that, the carry flag is set. Why does this happen? See, CMP, if you look at the, if you just, rewind the video 2-3 minutes back, you will find that I made you write 3 points. And there I clearly mentioned that if the content of the accumulator is smaller than the content of your operand register, then your carry flag will always be set, irrespective of the result of the operation. Okay, So the result of the operation will determine the value of the auxiliary carry flag and the parity flag and the sign flag, but it will not determine the value of the carry or the 0. These are determined separately. These are determined depending on the value of the registers. As a result, what will happen now is, now look at what will be the value of the parity flag. See how many ones are there? 1, 2, 3, 4, 5, 6. So there are even number of ones. So the parity flag will also be set. So in this way, your flags will vary after the execution of this instruction. Remember, we are not concerned about the result. The result that I've got there, the final result, 11110101. I'm not concerned about that result. What I'm concerned about is the comparison operation. The comparison operation will change my flags. Out of all the flags that are changed, I'm concerned only with the carry flag and the 0 flag. Okay, so what I'll do is, now I'll take up the CPI instruction. Okay, now let's look at this instruction CPI, compared immediate with accumulator. This is the next comparison instruction that we have. The previous one was CMP, where your operand, now the only difference between the previous comparison instruction and this comparison instruction lies in the way the operand is specified. In the previous instruction, we saw that the operand was set to be inside a register or in your memory location. Now here, the operand is set to be available to you immediately in the instruction itself. That's why it's called compared immediate with accumulator. And for the same reason, the addressing mode with respect to source is immediate, because the operand is directly available in the instruction. So that makes your addressing mode immediate. And with respect to the destination, it's implied because one of the operands is assumed to be the accumulator. Okay, now against the description, it will be exactly the same, only minor differences. So you please write down the description. I'll not be taking an example for this because it will behave in the same way as your previous comparison instruction. It will behave in the same way as CMP. And the only difference will lie in the way the operand is specified, just like I mentioned. So there, your operand will have to be specified. In the previous case, the operand was set to be inside a register. So I hope you have understood. Okay, now against the description, please write, the second byte is compared with the contents of the accumulator, full stop. The values being compared remain unchanged and the results of the comparison are indicated by setting the flags as follows. Give a colon, and in the next line, you will write down the same 3 points that you wrote for CMP. So you write those 3 points down, and after you've written them down, you please write, the comparison of 2 bytes is performed by subtracting the data byte from the contents of the accumulator, full stop. And against flags, please write down, all flags are modified to reflect the result of the operation. So I hope you have understood all the instructions in this video. If you have any doubts, please feel free to comment in the section given below. I'll see you in the next one. Thank you.